and your audience.
All right. So throughout the semester, we've talked about, of course, linear transformations, and in particular for one vector space to another. However, let's just say we're going to draw a diagram of vector space V. Let's say we have another one over here, W. Well, we can define, let's just say, we can define this transformation by the use of a function. We can call that function alpha, which is the transformation from vector space V to W. And that's represented by alpha. And any vector V in this space is transferred over here and symbolized by alpha of the vector V. However, let's just say we form another transformation onto the set of all real numbers. Well, there's such a transformation exists from vector space W to R. We can call that transformation T. And then T's transformation from W, vector space W, to the set of all real numbers. Well, if we transfer a vector over here, then perform this transformation over the set of all real numbers, well, we would get T of alpha of vector V. We're symbolizing that we have transforms over here. This works. However, suppose if we wanted to go from here to here. Well, of course, that can be symbolized by the composition of the transformations T and alpha. Well, this is a particular case for one particular function for a linear transformation. But what we can also do is define a new set. We can call that V star for the moment. Of course, not to be confused with the complex conjugate, the conjugate transpose. Well, V star is equal to a set of all the transformations from T to R, or from W, or from V to R, such that T is a linear transformation, of course, abbreviated. And that would encompass all the possible transformations from this vector space to this space. Well, this set is also vector space, although not proven. However, we can state that it is a vector space. And the way, of course, this would be proven is by chiefly, and the chief example of the proof by showing that it's a vector space would be, of course, by writing out the closure axioms and stating that there exists a zero vector. But this, of course, has a special name. And V star is the dual vector space of V. So, star is the dual vector space of V. And the vectors in this space, there are about three names for them, commonly called covectors. And but the thing is, not only can we define a new vector space, we can also define this function in a different way. We can just say that, and of course, would be denoted as alpha star. And the way that this transformation is structured is that it actually structured the transformation from the dual vector space of W to the dual vector space of V? Well, the dual vector space of W is all the transformations that go from W to R, and of course that encompasses for transformations from V to R. So this is still consistent with these transformations. And another thing to note is that not only, of course, for all these transformations, we can only use the vectors in V given for this new vector space. One thing to note, although it's not proved, yet to be proved, that the dimension of the dual vector space of V is equal to the dimension of the original vector space V. And of course, the way in which that would be proven would be by showing that the standard basis or a basis for each vector space contain the same number of elements, and showing that the basis for the dual vector space of V spanned the entire vector space, and of course was a linearly independent set of vectors. Of course, that's a relatively trivial proof that can be written out. However, this new function, this new linear transformation, has another special name for itself, and it's called the pullback map. It's the pullback map here. And I'll find that here. And the way I like to think about calling it a pullback is you're essentially kind of taking a step back, going essentially a different direction. That's the way, at least, I thought about the reason why it was called a pullback function. So, another thing to note is that the pullback of T by alpha is also, which is denoted as such, pullback of T by alpha, is also equal to the composition of the transformations of T and alpha, or T of alpha, and so on and so forth. And, however, another thing to note, of course, and the reason why I'm not proving these things is because, of course, they're rather trivial to write out. So, but the pullback function is also a linear transformation. Of course, this would be proven by showing that the properties of the addition between the transformations and scalar multiplication remain consistent with the transformation. And all this is just, we defined a new vector space, the set of all the linear transformations from vector space V to R, and this also constituted defining a function, a new linear transformation with relation to the original linear transformation. So, another example, a way to represent these transformations for the pullback, is that it can be represented by a matrix. So, one particular example is, let's just say, if we add alpha, transformation alpha from R3, and let's just say where this transformation is given by alpha of course, the elements. We have 3 elements for R3 vector space for each particular vector. Let's just say that was given by V1 plus V3. That will look like a 3. The second element is V3. And the third element is V2 minus V3. And this transformation from from here to the set of all real numbers, or in this particular case, it could be called where transformation is an element of the dual vector space of R3, where this is given by the elements, of course, of this vector space. We can introduce some notation, U1, U2, and U3. This would be given, all right, let's just say U1 minus 2 times U2, and plus U3. Well, going back up here, the pullback of T by alpha. Of course, this can be represented by 3 by 3 matrix. And for this particular case, we'll write this out, be T of alpha, by writing out matrix representation for each transformation and writing this out as well. Well, this is going to be represented by a 1 by 3 matrix. And that will, of course, be 1, negative 2, 1. And our 3 by 3 matrix for the transformation, the function alpha, will be a 3 by 3 matrix. 1, 0, 1, 0, 0, 1, and a 0, 1, negative 1. By performing four-sided matrix multiplication, what we will get is, of course, we'll also get a 1 by 3 matrix, which first entry will be 1, the second entry will be also a 1, and the third entry will actually be a, let's see, will be a negative 2. And this, of course, represents this transformation, or the pullback. This brings us all the way out to here. Well, this can be generalized to show a relation between the pullback of T by alpha, to the original matrix representation of the transformation. So if we write that out, I'll go ahead and move this board over here. And we can generalize that, of course, by using the standard basis of each vector space. So for R3, of course, standard basis will not change. However, it's appropriate to state a distinction for the sake of notation. It's the standard basis for R3. Consists of 3 vectors as such, as well as the second basis. So, which we can call that basis, the next basis for transformation over to R3, B prime. But in this case, B prime would be equal to the basis B. So B, of course, is basis, we can put that as B prime is equal to the original basis. Now, if we denote these, let's just E1, vector E1, E2, E3. Well, by representing this and applying the transformation, our transformation, to each particular vector, alpha of E1, well, by writing that out by our original example, we would of course transform over to the next basis. We can call those elements of B prime. Of course, they are equal to these vectors, we can call those vectors E1 prime, E2 prime, E3 prime, where, of course, each corresponding vector is equal to each other. Well, but by applying this transformation, what we will get is, of course, vector E prime of 1, this corresponds to this once it transforms over to R3, will be vector E1 prime plus vector E3 prime. And for the second one, of course, and this is due to that matrix. We'll write this out here in a moment. Of course, this corresponds to simply E vector E3 for the second element of the transformation of our vector, and the vector E3, that will of course correspond to E prime 2 plus, actually, minus E3 prime. Now by taking this information by what we've gotten by transforming each vector, the standard basis, over to the vector space, of course it's still the same vector space, well, what we would get is, of course, we represent that by the matrix, the pullback of alpha matrix with respect to the B prime basis, and B, of course, in which columns of A, well, the columns of A will be these entries. And we'll, of course, get 1, 0, 1, 1, 0, 0, 1, and 1, or 0, 1, and negative 1. However, of course, we look over there, think back to original matrix, this is simply the transpose of the original matrix. So, by seeing this relation, and of course, by seeing this relation, and by also, we can enact the second transformation, T, to this matrix, in which that would be denoted as such. Matrix alpha, pullback, with respect to basis B prime and B times T, of course, equal matrix 1, 0, 1, 0, 0, 1, 0, 1, and negative 1, times, of course, in this case, we will use the transpose or other linear transformation T, and that will, of course, be 1, negative 2, 1, and this will, of course, come out to be 1, 1, and negative 2, which, of course, is the transpose of the matrix T times the matrix linear transformation of alpha. And by seeing this generalization, we know that, of course, the transpose property, such as we have two matrices, A and B. This is equivalent to B transpose times A transpose. Well, this right here be equivalent to transpose of linear transformation alpha, represented by a matrix, and times the transformation T is transpose. And of course, this is this exact operation. So, of course, this generalizes the matrix representation and the relation of representing the transformation by either the pullback or the original transformations. Okay, So, with that, another thing, I'd like to move on to, of course, talking about multilinear mapping. And what I would do, of course, is, let's just say if we had a set of n many vector spaces, such as from V1 to Vn, well, but what we can do is, if we apply the Cartesian product, which would be, of course, by taking all, of course, ordered vectors in each particular set, this product will be equal, or is equal to, the set of all pairs of vectors V1 and Vn, such that Vi is an element, of course, corresponding vector space, Vi, and, of course, let's see, and this, of course, applies from I equals 1 to n. Well, suppose if we want to see what we can do with the transformation. So if we utilize this product, this transformation of these vectors to another vector space, we write that out. This is defined as such. It's a transformation which, of course, the only way in which would this be so is if this is a vector space. And of course, it can be verified as such by showing, of course, again, the closure axioms and such. And if we apply like the transformation from this vector set, this set, we can denote it as a vector space for this transformation. This is a multilinear transformation if the corresponding components of this transformation are linear. So let's write that out for, of course, a bit of verification. And let's call this set V. Well, if we apply this transformation, V W, well, suppose if we have, of course, T of V1 plus some other vector x all the way to Vn. Well, verified that this is, that each component is linear. This would distribute this transformation V1 Vn plus transformation of vector x plus Vn. I should have wrote a V2 right there, but we can move on to, of course, down to the last vector, n. We denote that as T of V1 to Vn minus 1. And then we have vector Vn plus some other vector, we can use the same, plus x. And this is equal to T of V1 Vn minus 1 Vn plus transformation of vector V1 Vn minus 1 and the vector x. That's for property of addition. Well, to verify, of course, property of scalar multiplication. You can write that as such, and I'll use a new board. Let's just use some scalar, c, where c, of course, is an element, set of real numbers. Well, t of c times v1, vn equals c times transformation of vectors v1 through vn, because, of course, each component must be linear, or for this be a multilinear mapping. This corresponds all the way down to the last vector, v1, c times vn. This is equal to c times the transformation of v1, vector v1, vn. Of course, so long as these remain true, then this is a multilinear in multilinear form, or multilinear mapping. And of course, that corresponds to a certain number of vectors. However, if each component of that Cartesian product was the same vector space, such as if each vi in this set in Cartesian product v1 through vn are the same, then the transformation of v cross v is the multilinear in form of v. And of course, this anticipates the next thing we're going to talk about, which is, of course, bilinear mapping, or the bilinear form. Another thing, of course, that's cool about multilinear mapping is, of course, the basis of what a tensor is. Of course, assuming that you can make it through the indices and the notation. But for a particular example, let's just say if we had the transformation of simply v cross v to the set R, and this is a multilinear in form. Forgot to mention, if this transformation goes to the set of R, set of all real numbers. So for this particular set, this is the bilinear, also known as a bilinear mapping for the on vector v. And to give a particular example of a bilinear mapping, let's just say if we had a function f0 of two particular vectors, call them u, and vectors u and v. We can define this function as such for each ith element of u and v, which we would have v1 times v1 plus un times vn, where of course u, the elements of u are ranked from u1 to un. They're not ranked, but that's each component. And of course that corresponds to vector v. And this of course is the dot product for any particular vector or of a particular dimension. And what we can also do is, of course, this can be this is also, I will mention, f0 is the transformation Rn cross Rn to to, of course, the set of all real numbers, because, of course, we're going to get a number for an answer here. And this is just one particular example of a bilinear mapping. There are many more, of course, for matrices and such. But